Hi, dear students. Already, I have discussed about the some theorems of cosets, and in previous video, I already say about that. Uh, we will discuss theorem 6, 7, and 8 in new video, and especially Lagrange theorem in theorem 7 is very important, and it is to be discussable in this video. Now I will start the topic. Here, theorem number 6, you can see that it is written in form that let H be a subgroup of a group G. The relation rho defined on G by A rho B if and only if A inverse B belongs to H for A comma B belongs to G is an equivalence relation on G. At first, starting this, you have to know about the equivalence relation. You already know that what is equivalence relation. A set, any set, any set, if it continues three type of relation. One is reflexive, one is symmetric, and one is transitive. That three type of relation, if S considers with a relational operator rho or a relational operator r, anything, then we can see and we can say that is equivalence relation with respect to this relation r. In case of reflexive, you already know that in case of reflexive, I will speak about reflexive first. In case of reflexive, if A belongs to S implies A comma A belongs to rho, that is A rho A. If A is rho related with A, where A is an element of S, then we can say rho is a reflexive relation about the set S. Here, for this, you can say let A be an element of the group G, okay, then G must be a set, and it is more about that, that is G is a group. If G is a group, then A inverse already exists in G, and we can write like this that A inverse into A is equals to E. We know already A inverse A equals to an identity element, and identity element E is belongs to H, as because E is an identity element of the group H, as E is the identity element which belongs to G, and H is the subgroup of G, so E is also identity element of H. We already discussed about this in previous theorems. So E belongs to H. Now E belongs to H, that means A inverse A belongs to H. A inverse A is in the form of A inverse B. So we can say that A row B relation, A row B, here in place of B we also put A. Okay, by this concept, A inverse A belongs to H and inverse B belongs to H. If A row B, then in that case A is in place of B, so we can say that A row A, that is A is row related with A, so row is reflexive. Okay, now in case of symmetricity, we know if A row B holds, that is A comma B belongs to row actually, then we have to show that B comma A also belongs to row, that is B row related with A. Okay, for this we first take the let A comma B two elements of G, and A row B holds, that is A row B holds, that is A inverse B belongs to H, that is A inverse B belongs to H. If an element belongs to H, any element, if any element belongs to H, then its inverse also belongs to H, as H is a group, so its inverse obviously belongs to in that group. So A inverse belongs to H, so we can write this element's inverse so also belongs to H. Now inverse property we can write B inverse, here A inverse whole inverse belongs to H, A inverse whole inverse is equals to A, so we have B inverse A belongs to H, that is B row A holds. We considers A row B holds, now we get A B row A holds, so row is symmetric. Okay. Now in case of transitivity we have to take three elements. Here you can see the three elements are A, B, C belongs to G, and we have to take that A row B holds and B row C holds. That is A row B holds. That is we have A inverse B belongs to H, and already have B inverse C belongs to H, and we have to prove that A row C holds. A row C holds. Now we have A row B belongs to H, B row C belongs to H. So by closure property, two elements with composition, two elements composition is also belongs to H by closure property we can say. So we have here by associative law B inverse C, B inverse equals to E, A E C belongs to H. So we have A inverse C belongs to H, as E is identity element, so we can write this A inverse C belongs to H. Here we have A row C holds, so A row C holds by these conditions, as A inverse C belongs to H, so A row C holds. So in property A row B row C holds, so and also we have A row C holds, this means row is transitive. Here row is reflexive, symmetric and transitive, so row is equivalence relation. Okay. Now I will discuss about the Lagrange theorem, theorem number 7, very important theorem. The order of every subgroup of a finite group G and divisor of order of G. What we will say? That the order of every subgroup of a finite group G is a divisor of order of G. Okay. Now you can see proof. Let H be a subgroup of finite group G and order of G is n, that is O of G equals to n. Let us consider the set of all distinct left cosets of H in G. Since G has finite number of elements, here you can see it is a finite group, so G has a finite number of elements here and number of members, then number of distinct left coset in G is also finite. As G is a finite number of elements, then we can say that the number of left cosets in G is also finite, as because if we are finite number of members in a room, if we finite number of members, then varieties type of permutation combinations of varieties type of characters will be, it will be fixed, it will be finite, you can say that. So it is given property, the number of distinct left coset in G is also finite, you can say, as the number of members are finite, so it is also finite. Again we know any two left coset of H in G are either distinct or identical. It is a previous theorem which is discussed in the previous video, either distinct or identical. Let there exist some element x1 x2 up to xm, up to x suffix m, xm in G such that x1h x2h xmh are complete list of distinct left cosets of H in G. As left cosets of H, it will be fixed, it will be finite, so we take the elements in G is x1 x2 up to xm, so left cosets of H is also x1h, x2h up to xmh. Okay. So we can say by partition of group theory that G must be what G must be. If it is G, then G must be here x1h, here x2h, here x3h, here x4h, and like this x dot dot xmh. So G is the additions of all left cosets or any other left subsets. Okay. Then you can write that G is equals to x1h union x2h union dot 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 union xmh, as G is the addition of all left causes. So you can write this. Okay. Now we know every left causes of H has some number of elements as that of H. That is, if in H if in H three elements, then in a left cosets of H at x1h it also have three elements. If in H have like this type of element A, B, C, then in x1h what type of element x1a, x1a, comma x1b, comma x1c. So x1h also contains three elements, x2h also contains three elements, as xmh also contains three elements. So it must be, we can say, every left coset of H has same number of elements as that of H. That is, if H contains three elements, then every left coset of H also contains three elements. So order of every left coset is equal to order of H. Okay. Here m number of left cosets. Here m number of left cosets, and we already have G is summation of m number of left cosets. Okay. So what you can write, that is order of G. Okay, I write it. It's order of x1h plus order of x2h plus dot 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 order of xmh. Okay, here order of x1h is OH, order of x2h is OH, order of xmh is also H. So we can write order of G equals to OH plus OH plus dot 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 OH. Okay, here m number of OH as m number of left causes. So we can write m into H, m number of same elements, we can write m into that elements. That is, if we have 3 plus dot 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 3 as 5 times, then we can write 5 into 3. Here in place of 5 we have m, in place of 3 we have order of H. So we can write order of G equals to order of H. Okay. So we have order of G equals to m into order of H. That means order of H divides order of G. As because if we can write that 6 equals to 2 into 3, 2 into 3. Here in place of m have 2, in place of H we have 3. Then we can write that 3 divides 6. Okay. This is the Lagrange theorem. Very important theorem. Very easy theorem, but very important. That is, the order of every subgroup of a finite group G is divisor of order of G. Where is it? Now, theorem number 8. Every group of prime order is cyclic. Every group of prime order is cyclic. Proof. Very important. It is also very important. Let G be a group of prime order P. Let G be a group of prime order P. It is prime, which number or which integers is only divisible by 1. None other than that, and no other elements, only divisible by 1, and that elements, obviously, and that elements, that is 7. 7 is divisible by 1 and itself is by 7. So 7 is prime. So proof, let G be a group of prime order P. So order of G equals to P is a prime order or prime order, and obviously it is greater than 1. Let A be a non-identity element of G. As A be a non-identity element, then we can say that A not equals to E. A not equals to E, as E is the identity element, but we have taken A is non-identity element of G, so A not equals to E. Let us consider a cyclic subgroup H of G generated by A. If we take that the cyclic subgroup is generated by E, that is identity element, then the theorem is over there, as because E is equals to 1 and 1 is prime, order is cyclic obviously. So we cannot choose that that the cyclic subgroup H can be generated by identity element E. So we must have taken a non-identity element, and we also must have taken that there is a cyclic subgroup H of G generated by A. So obviously order of H greater than 1, as because A not equals to E, E represents 1, so A cannot be 1. As A cannot be 1, then must be order of H cannot be 1, so order of H must be greater than 1. Okay, now H is a subgroup of G, and order of G, which is finite, order of G is P. Here order of G is which is finite, as P is a prime number is a finite number, must be. Okay, then by Lagrange theorem, that is in previous theorem, we can write that order of H divides order of G, and it is implies order of H divides P, as order of G is P. Okay, then either order of H is equals to P or order of H equals to 1. Why? As because uh, at previous I have already said that uh, we have already taken an example of 7. 7 is a number which is divisible by 1 and itself, that is 7, and it is the main definition of prime, that is any prime number is must be divisible by 1 or itself. So we can write that order of H equals to either 1 or order of H is equal to P, that is only 1 can divide P or P can divide P, none other than that, as P, as because P is a prime number. Okay, so we can write order of H equals to P or order of H equals to 1. Now here we have already uh, can write that order of H is greater than 1. So order of H cannot be 1, cannot be equal to 1. It is not possible, as order of H greater than 1. Already we have can consider, we can already written this. So obvious order of H greater than 1. So there has none other option, so order of H is equals to P. It is the only possibility we have, so there is no possibility except order of H equals to P. So order of H is obviously equal to P. So here we already have order of G equals to P, and we already have order of H also P. So order of G equals to order of H, order of G equals to order of H. Okay, if order of G is equals to our order of H, that is where a G H, H is a subgroup of G, and if order of G equals to order of H, it is happen only when G is cyclic group generated by A. It is only when if G is cyclic group generated by A. It is already discussed at the time of cyclic group. Okay, now I will discuss about normal subgroups and its property in very next video, and waiting for this video. Okay students, bye.